December 7th, 1942. Captured American B-17 wreckage site, 40 kilometers southwest of Bremen, Germany. Oberst Klaus Richter knelt in the frozen mud, staring at a piece of American bombing equipment that shouldn't exist. The device was still intact despite the crash. A complex assembly of gyroscopes, mirrors, and precision gears housed in a stabilized mounting. Within 72 hours, this Luftwaffe bombing tactics officer would witness test results that contradicted everything German strategic bombing doctrine had assumed about American technological capability. American heavy bombers had been hitting targets with accuracy the Luftwaffe's intelligence analysts had declared mathematically impossible. Richter's own bomber crews reported seeing American formations drop ordnance that struck within meters of intended targets, from altitudes above 6,000 meters. The Luftwaffe had dismissed these reports as exaggeration, the natural tendency of combat pilots to overestimate enemy effectiveness. Standing in the wreckage of this B-17, holding what appeared to be an impossibly sophisticated automatic bomb sight, Richter understood the reports had been accurate all along. By December 1942, the American 8th Air Force had conducted only limited operations over occupied Europe, but the bombing accuracy data was already troubling German analysts. Standard Luftwaffe bombing doctrine, based on 5 years of combat experience from Spain through the Eastern Front, held that level bombing from high altitude could achieve accuracy of approximately 200 to 300 meters under ideal conditions. German bombers typically operated between 3,000 and 5,000 meters altitude, where anti-aircraft fire remained effective, but bombing accuracy was acceptable. The Americans were bombing from 6,000 to 7,000 meters, altitudes where German doctrine said precision was impossible. Yet they were achieving accuracy. The Luftwaffe couldn't match at half that height. The numbers from Luftwaffe damage assessment reports painted a disturbing picture. American raid on Rouen rail yards, October 9, 1942. 94% of bombs within 300 meters of aim point. Estimated bombing altitude 6,200 meters. American raid on Lille Locomotive Works, October 9, 1942. 88% of bombs within 200 meters of aim point. Estimated bombing altitude 6,000 meters. American raid on U-boat construction facilities at Saint-Nazaire, November 17, 1942. 79% of bombs within 150 meters of aim point, despite heavy cloud cover and fighter opposition. Estimated bombing altitude 6,500 meters. These accuracy figures exceeded what German bombers could achieve at 3,000 meters altitude, with experienced crews and no opposition. Oberst Klaus Richter had commanded bomber squadrons during the Battle of Britain and the early phases of Operation Barbarossa. He'd personally led over 120 combat missions in Heinkel. He won 11s and Junkers Ju-88s. He'd seen firsthand the practical limitations of level bombing. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. His experience had taught him brutal lessons about bombing accuracy, weather, altitude, airspeed, aircraft vibration, human reaction time, every variable degraded precision. The Luftwaffe had developed standardized accuracy expectations based on thousands of combat missions. Low-altitude bombing, 500 to 1,000 meters. Expected accuracy, 50 to 100 meters circular error probable. Used primarily for tactical targets, when fighters and flak allowed such dangerous approaches. Medium-altitude bombing, 2,000 to 4,000 meters. Expected accuracy, 150 to 250 meters, circular error probable. The standard Luftwaffe bombing profile, balancing accuracy against defensive fire effectiveness. High-altitude bombing, above 5,000 meters. Expected accuracy, 300 to 500 meters, circular error probable. Rarely used because accuracy degraded to near uselessness, while fuel consumption increased dramatically. The American bombing at 6,000 meters plus should have produced circular error probable of 400 meters or worse. Instead, they were achieving accuracy better than German medium-altitude bombing. Richter had argued in tactical meetings that the Americans must be using different bomb release methodology, perhaps diving attacks from high altitude, similar to Stuka tactics. Reconnaissance photos proved him wrong. American formations remained in level flight throughout bomb runs. No diving, no altitude changes that would indicate manual bombing techniques, perhaps specially trained bombardiers with exceptional skill. Intelligence reports on captured American aircrew indicated bombardier training lasted approximately 12 weeks. German bombardier training took 6 months and produced crews who couldn't match the American results. Something else was enabling the accuracy. Richter had been assigned to investigate captured American bombing equipment after intelligence officers in Berlin demanded answers. German High Command wanted to know if American accuracy resulted from superior training, superior tactics, or superior technology. The answer would determine German strategic bombing development for the remainder of the war. On December 5, 1942, a badly damaged B-17 had crashed near Bremen after a raid on U-boat facilities. The aircraft's bombardier had been killed instantly, but the forward fuselage section where he'd been stationed remained relatively intact. Richter had arrived at the crash site with a team of Posani, Luftwaffe technical specialists on December 7th. What they found in the bombardier's position changed everything. The device was immediately recognizable as an automatic bomb sight, but the complexity far exceeded anything in German service. German bombers used the Luftfernrohr 7, introduced in 1937 and considered adequate for Luftwaffe bombing doctrine. The Lotfe 7 was a mechanical computing site that calculated bomb release points based on altitude, airspeed, and ballistic characteristics. It required the bombardier to manually track the target through a telescope, input the aircraft's parameters, and release bombs when the site indicated correct geometry. The Lotfe 7 was effective within its design parameters, but it had significant limitations. Manual tracking meant human error directly affected accuracy. Any aircraft movement or vibration during the bomb run degraded precision. The bombardier needed clear visual contact with the target throughout. The approach. The American device was fundamentally different. Richter examined it carefully, noting construction details that revealed sophisticated engineering. The site mounted on a gyro-stabilized platform that automatically compensated for aircraft movement. Multiple gyroscopes provided 3-axis stabilization, maintaining site alignment regardless of turbulence or course corrections. An elaborate system of mirrors and lenses created an optical path from the telescope to the bombardier's eyepiece. The critical difference was apparent immediately. This site actively stabilized itself against aircraft motion rather than requiring the bombardier to compensate manually. A complex mechanical computer occupied the site's central housing. Richter counted dozens of precision gears, cams, and linkages that appeared to calculate ballistic trajectories automatically. Input dials allowed setting altitude, airspeed, wind direction, wind speed, and bomb ballistic characteristics. The computer appeared to continuously calculate the correct bomb release point as these parameters changed during the approach. Most significantly, the site connected directly to the aircraft's autopilot system. The bombardier could literally fly the aircraft during the bomb run by adjusting the site. As the site tracked the target, it sent electrical signals to the autopilot, making small course corrections automatically. The bombardier didn't need pilot coordination for precise bombing. He controlled everything through the site itself. Richter had never seen anything comparable in German service. The Lotfe 7 was a mechanical calculator that assisted the bombardier. This American device was an integrated automatic bombing system that removed human error from the equation. The implications were staggering. If this device performed as its design suggested, American bombing accuracy wasn't the result of superior training or tactics. It was pure technological advantage applied to the bombing problem through industrial precision engineering. Richter ordered the device carefully removed from the wreckage and transported to the Luftwaffe test facility at Rechlin. He wanted controlled tests to determine actual performance capabilities. While technicians extracted the bomb site, Richter examined the rest of the B-17's forward compartment. What he found reinforced his growing understanding of American technological approach. The bombardier's station was equipped with heated flight suit connections, oxygen supply with backup systems, and sophisticated intercommunications equipment connecting him directly to the pilot and navigator. The entire compartment was designed around the assumption that bombardiers would operate at extreme altitude for extended periods while maintaining complex calculations. German bomber design philosophy prioritized simplicity and maintainability. Complex systems meant more maintenance, more potential failures, more logistics burden. Americans had chosen the opposite path, accepting maintenance complexity to achieve operational capability. The bomb site arrived at Rechlin on December 10th. Luftwaffe engineers spent 2 days examining the device, photographing every component, and attempting to understand the mechanical computing system. Chief Engineer Hermann Schultz provided the preliminary assessment. This site represents approximately 5 to 7 years of advanced development beyond current Luftwaffe capability. The gyro stabilization alone requires manufacturing precision we cannot currently match in production quantities. The mechanical computer uses gear tolerances measured in thousandths of a millimeter. We can produce similar precision in laboratory conditions, but industrial-scale production would require retooling we don't possess. Richter read the report with growing concern. The assessment confirmed his field observations. This wasn't slightly better technology. This was a generational gap in precision engineering. Schultz continued. Most concerning is the integration with autopilot systems. This requires electrical servo motors with response times faster than human reaction capability. The Americans have clearly invested substantial resources in electromechanical control systems. We are only beginning to explore similar technology. Richter asked the critical question. Can we test it functionally? Schultz hesitated. We can bench test the mechanical systems and verify the calculations. We can measure gyro stability and optical alignment, but actual bombing tests require installing it in an aircraft with compatible autopilot systems. We don't have such systems. Richter made the decision immediately. Install it in a captured B-17. We have 3 in flyable condition. Use the intact aircraft systems. I want real bombing tests with German crews operating American equipment. I need to know if this device actually delivers the accuracy we're seeing in combat. The test program took 8 days to organize. Luftwaffe engineers installed the recovered bomb site in a captured B-17 that had landed intact in France after becoming lost in fog during a raid in August. The aircraft had been repaired and was being used for evaluation flights. A Luftwaffe test crew was assembled. Major Wilhelm Braun, experienced bomber pilot with over 300 combat missions. Hauptmann Ernst Fischer, bombardier with 5 years' experience on Lotfe 7 site. 4 additional crew members qualified on captured American aircraft systems. December 22, 1942, Rechlin Test Range. The captured B-17 took off at 900 hours, carrying 12 practice bombs. The test protocol was straightforward. Fly-level bombing runs at 6,000 meters altitude against marked target panels. Release bombs using the American bomb site exactly as U.S. bombardiers would use it. Measure accuracy and compare to standard Luftwaffe results at equivalent altitude. Hauptmann Fischer had spent 3 days learning to operate the Norden site, as intelligence had identified it. The American instruction manual had been recovered partially intact, and German translators had worked through the technical English to produce operational guidelines. Fischer reported the learning curve was steeper than expected. The site required understanding 3-dimensional geometry and continuous calculation adjustments that the Lotfe 7 automated differently. But the actual bombing procedure was methodical once understood. The test run proceeded as follows. At 6,000 meters altitude, Fischer activated the site and began tracking the target panel 5 kilometers ahead. He input altitude 6,300 meters, accounting for air pressure variations, airspeed 280 kilometers per hour, wind from northwest at 35 kilometers per hour, bomb ballistic characteristics for standard German practice bombs. The site's mechanical computer began, calculating the bomb release point continuously, adjusting as the aircraft approached the target. Fischer engaged the autopilot coupling. The site immediately began making small course corrections, keeping the aircraft aligned with the target despite crosswind. Fischer watched through the eyepiece as the target image remained perfectly centered despite aircraft movement. The gyro stabilization worked exactly as designed. At the calculated release point, the sight automatically triggered bomb release. Fisher felt the aircraft lift slightly as the practice bombs dropped away. From the ground, Richter and the technical staff watched through binoculars. The bombs fell in a tight pattern, all impacts within a circle approximately 50 meters in diameter. The center of impact was 23 meters from the target panel center. Fisher made 4 more bombing runs at 6,000 meters altitude. The results were consistent. Run 2. Impact center 31 meters from target. Run 3. Impact center 18 meters from target. Run 4. Impact center 41 meters from target. Run 5. Impact center 27 meters from target. Average circular error probable, 28 meters at 6,000 meters altitude. Richter stood silently, watching the impact patterns. He just witnessed accuracy that exceeded standard Luftwaffe medium-altitude bombing while operating at twice the altitude. The American bomb sight wasn't incrementally better. It was categorically superior. That evening, Richter reviewed the test data against Luftwaffe combat statistics. Standard Luftwaffe bombing accuracy at 6,000 meters altitude, circular error probable 300 to 400 meters, best recorded accuracy by experienced crews, circular error probable 180 meters. American Norden bomb sight operated by Luftwaffe crew, with 3 days training, circular error probable 28 meters. The technology gap represented a 10-to-1 advantage in precision. If American bombardiers trained for 12 weeks on this site could achieve similar or better results, the implications for strategic bombing were devastating. German industrial targets were vulnerable to precision attack in ways Luftwaffe doctrine had never anticipated. Richter spent the following days analyzing exactly how the Norden achieved its remarkable precision. The key was integration of multiple technologies into a unified system. The gyroscopic stabilization platform was the foundation. 3 gyroscopes, 1 for each axis of motion, maintained a stable reference frame, independent of aircraft movement. The gyros spun at 18,000 revolutions per minute, their angular momentum resisting any attempt to change orientation. This meant the bomb sight maintained perfect alignment with the ground, regardless of how the aircraft pitched, rolled, or yawed. The mechanical computer was equally sophisticated. A series of interconnected gears and cams performed continuous analog calculations based on input parameters. As the bombardier adjusted dials for altitude, airspeed, wind, and ballistics, the computer recalculated the bomb trajectory in real time. The computer wasn't just calculating a single release point, it was continuously solving differential equations that predicted where bombs would fall given current conditions. The mathematics were complex enough that German engineers needed 2 days just to understand the gear ratios. The autopilot integration was perhaps most revolutionary. The bombardier controlled a small handwheel on the sight that sent electrical signals to servo motors in the autopilot system. These motors made tiny adjustments to the aircraft's control surfaces, keeping the plane precisely aligned with the target. The pilot essentially surrendered control to the bombardier during the bomb run. This eliminated the coordination errors that plagued German bombing. With the Lotfe 7, the bombardier had to verbally direct the pilot, turn left 2 degrees, steady, hold this heading. Every instruction introduced delay and interpretation error. With the Norden, the bombardier's adjustments translated instantly into aircraft movement. The human communication delay was eliminated. Richter calculated the cumulative effect of these advantages. Gyro stabilization reduced pointing error by approximately 70% compared to manual tracking. Continuous trajectory calculation reduced ballistic error by approximately 60% compared to single-point calculations. Autopilot integration reduced pilot coordination error by approximately 80% compared to verbal instructions. The combined effect wasn't additive, it was multiplicative. Each improvement enhanced the others, creating accuracy that exceeded the sum of individual components. German engineers attempted to reverse engineer the Norden's key technologies. The gyro stabilization platform proved impossible to replicate with existing German manufacturing capability. The gyroscopes required bearings with tolerances measured in microns. German precision instrument manufacturers could produce such bearings individually in laboratory conditions, but mass production required grinding machines Germany didn't possess. The mechanical computer's gear train used hardened steel gears with teeth cut to tolerances of 0.005 of a millimeter. German gear cutting machines could approach this precision, but not maintain it across production runs of thousands of units. The variation between individual sites would be too great. The autopilot servo motors required electrical response times of 50 milliseconds or less. German electromechanical technology in 1942 could achieve response times of approximately 200 milliseconds, fast enough for some applications, but not fast enough for precision bombing autopilot coupling. Every technical analysis reached the same conclusion. Germany could theoretically build a Norden equivalent, but only in small quantities using laboratory methods. Industrial-scale production would require retooling that would take years and consume resources needed for existing weapon systems. Richter requested production intelligence on the American bomb site from Abwehr, German military intelligence. The report arrived December 28 and contained information that made the tactical problem worse. Estimated American Norden bomb site production, approximately 800 to 1,000 units per month as of mid-1942. Estimated total production through December 1942, approximately 12,000 units. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Production rate accelerating as American aircraft manufacturing expands. Estimated production capacity by end of 1943, 1,500 units per month. The Americans weren't just building better bomb sites, they were building them at industrial scale that matched their aircraft production. German Luftwaffe 7 production, approximately 300 units per month. Total production through December 1942, approximately 18,000 units, serving all Luftwaffe bomber needs. German production capacity was adequate for Luftwaffe requirements, but there was no capacity to develop and produce new advanced site designs at scale. The Norden represented perhaps 5 years of development time Germany didn't have, and production capacity that would require retooling Germany couldn't afford. The intelligence report included additional disturbing details. American Norden production involved multiple manufacturing facilities, primary assembly at the Norden factory in New York, gyroscope production at specialized instrument manufacturers, optical components from precision lens makers, electrical components from electronics, contractors. The distributed production meant no single facility was critical. If one plant was damaged, others could increase output to compensate. This was American industrial philosophy applied to military technology. Redundant production capacity, distributed manufacturing, specialized contractors, all coordinated through standardized specifications. Germany's precision instrument industry was concentrated in a handful of facilities: Zeiss for optics, Bosch for electronics, specialized machine tool makers in Stuttgart and Munich. Bombing any of these facilities would cripple German capacity to produce equivalent systems. Richter analyzed the strategic implications. The Norden bomb site gave American heavy bomber formations capability to strike specific buildings within large industrial complexes from altitudes where fighter interception was difficult and flak was less effective. German strategic bombing doctrine was based on area bombing, hitting general industrial zones or cities, rather than specific facilities. The Luftwaffe had developed this doctrine because German bombing accuracy didn't support precision strikes. The Americans had developed technology that made precision possible, then built doctrine around that capability. The difference wasn't just tactical, it was philosophical. German bombing focused on terrorizing populations and disrupting general industrial capacity. American bombing could destroy specific ball-bearing factories, specific oil refineries, specific aircraft plants. One approach required massive tonnage dropped across large areas. The other approach achieved strategic effect with precise tonnage on critical targets. The tonnage comparison made the problem worse. A German bomber formation might drop 100 tons of bombs across a 2-kilometer square area, damaging everything inside but destroying nothing completely. An American formation could drop 100 tons of bombs into a 400-meter square area, completely, destroying everything inside. The destructive efficiency was exponentially higher. Richter included these calculations in his report to Luftwaffe High Command. The report was classified secret and distributed to tactical planning officers throughout the bomber command structure. The conclusions were sobering. American precision bombing capability represents fundamental threat to German industrial war production. Current Luftwaffe fighter defense doctrine assumes American formations will bomb general urban areas where damage is dispersed. If Americans can consistently strike specific critical facilities, defense must concentrate around those facilities rather than broad area coverage. German bombing doctrine requires immediate revision. Area bombing of British and Soviet industrial targets has not achieved strategic results commensurate with resources expended. American precision approach may prove more effective with fewer aircraft and lower losses. Recommendation: prioritize development of German advanced bombsight technology and gyro-stabilized platforms for medium and heavy bomber use. Estimate 5 years minimum development time to match current American capability. The recommendation went nowhere. By December 1942, Germany was fully committed to wartime production of existing designs. Developing new systems required resources that didn't exist. The decision was made to improve Lotfe 7 incrementally rather than attempt to match Norden sophistication. The result was predictable. German bombing accuracy remained essentially unchanged throughout the war. American bombing accuracy improved, as bombardier training incorporated more sophisticated Norden tactics, and as bomb ballistics were refined to match site calculations. Richter documented the divergence throughout 1943 and 1944. German bombing of Soviet industrial targets, circular error probable 200 to 300 meters at medium altitude, 300 to 500 meters at high altitude. American bombing of German industrial targets, circular error probable 75 to 150 meters, consistently from altitudes above 6,000 meters. The precision gap translated directly into strategic effectiveness. American raids on ball-bearing plants at Schweinfurt destroyed 67% of German ball-bearing production capacity, despite hitting only specific factory buildings in 2 raids. German raids on Soviet tank plants required dozens of missions to achieve similar production disruption, because bombs fell across entire industrial districts, rather than concentrating on specific facilities. The Schweinfurt raids demonstrated Norden precision at its most devastating. The ball-bearing plants were located in a dense urban area surrounded by residential neighborhoods and non-critical industrial facilities. Area bombing would have destroyed the entire district, killing thousands of civilians and damaging hundreds of buildings to eliminate the ball-bearing plants. American precision bombing struck the specific factory buildings housing grinding machines and assembly facilities, while leaving surrounding areas largely intact. Post-raid reconnaissance showed the destructive efficiency. Factory building number 12, direct hit, roof collapsed, interior machinery destroyed. Factory building number 13, direct hit, complete structural failure. Factory building number 19, 2 direct hits, fires consumed remaining equipment. Administrative building adjacent to factory number 12, undamaged. Worker housing 200 meters from factory number 13, minor blast damage only. The bombs had fallen exactly where aimed. The Norden bomb site wasn't just better technology, it was technological advantage that enabled different strategy. American doctrine could target the critical nodes in German industrial production: bearings, oil refineries, aircraft engine plants, electrical transformer stations, destroying them with tonnage that would have merely damaged them through area bombing. The mathematical advantage was overwhelming. A German bomber stream dropping 1,000 tons of bombs across Berlin's industrial sectors might reduce production by 10% temporarily. An American formation dropping 1,000 tons of bombs on 3 specific factories could eliminate 30% of production in those particular industries permanently. The efficiency ratio meant American strategic bombing achieved greater effect, with fewer sorties, fewer losses, and less resource expenditure. Richter watched this reality unfold through 1943 and 1944 as American daylight raids systematically dismantled German industrial capacity. The raids followed a pattern that Lotfe 7 bomb sites couldn't match and German fighters couldn't prevent. High-altitude approach above 6,000 meters where flak was less accurate and fighter interceptions required extensive fuel to reach. Tight formation flying that concentrated defensive firepower against German fighters. Precision bombing runs that placed high explosive ordnance directly on machine tool facilities, not randomly across factory districts. Post-raid reconnaissance showing specific buildings destroyed while surrounding areas remained untouched. The Norden bomb site had given American strategic bombing the capability to conduct true precision war against industrial targets. German strategic bombing remained area attack that achieved results through volume rather than accuracy. By January 1945, Richter had compiled comprehensive analysis of the bombing accuracy gap and its strategic consequences. His report documented the full scope of American technological advantage, Norden bomb site characteristics, gyro-stabilized platform, providing 3-axis stabilization independent of aircraft movement, mechanical analog computer calculating bomb, release point continuously based on multiple input variables, autopilot integration, allowing bombardier to fly precise course corrections during bomb run, optical system providing clear target image regardless of aircraft attitude, production rate of 1,500 units per month, sufficient to equip all American heavy bomber production. German Lotfe 7 characteristics, mechanical computing site requiring manual target tracking, no gyro stabilization, accuracy depends on aircraft stability during bomb run, no autopilot integration, requires close pilot-bombardier coordination. Simple optical telescope without image stabilization. Production rate of 300 units per month, adequate for current needs but no capacity for advanced development. The capability gap represented technological divergence of approximately 5 years. The Americans had invested in precision engineering and industrial-scale production of complex electromechanical systems. Germany had focused on simpler systems that could be produced reliably with existing manufacturing capacity. Both approaches made sense within their strategic contexts. Germany needed large numbers of adequate bombers to support tactical operations and area bombing campaigns. America needed smaller numbers of highly capable bombers to strike specific strategic targets. The difference was sustainability. German doctrine required continuous replacement of bombers lost to defenses during area bombing raids that achieved limited strategic effect. American doctrine accepted high initial losses, but achieved strategic effect that justified the expenditure. By 1944, American bomber losses declined as German fighter strength eroded, while bombing accuracy improved as bombardiers gained experience with Norden tactics. The strategic bombing campaign became self-sustaining. Precision attacks on German aircraft plants reduced fighter production. Reduced fighter strength meant lower American bomber losses. Lower bomber losses meant more experienced crews conducting more accurate raids. More accurate raids meant greater damage per ton of bombs dropped. The positive feedback loop, enabled by Norden precision capability, systematically destroyed German ability to resist. Richter's final assessment was grimly accurate. The American Norden bomb site represents technological advantage that cannot be countered with current German resources. Accuracy of 75 meters at altitudes above 6,000 meters enables precision attack on any German industrial target visible from the air. German fighter defenses cannot prevent American bombers from reaching targets. German flak defenses cannot protect every critical facility simultaneously. German industrial capacity cannot repair damage faster than American raids inflict it. The Norden bomb site, combined with American industrial production capacity, represents war-winning advantage in strategic bombing. Oberst Klaus Richter survived the war and was captured by American forces in May 1945. During interrogation, American intelligence officers were surprised by his detailed knowledge of Norden bomb site capabilities. Richter explained about the December 1942 testing and the subsequent analysis. The American officers confirmed his accuracy figures were essentially correct. Post-war analysis documented the full scope of American Norden bomb site production and deployment. Total Norden bombsights produced during World War II, approximately 50,000 units. Total American heavy bombers produced during World War II, approximately 34,000 aircraft. Production capacity exceeded aircraft production, ensuring every bomber had operational site with spares for maintenance. Estimated total bombs dropped using Norden guidance, approximately 1.4 million tons on European targets. Average circular error probable for Norden-directed bombing throughout the war, approximately 230 feet at altitudes above 20,000 feet. In optimal conditions with experienced crews, accuracy improved to 75 feet, circular error probable. The German Luftwaffe 7 never achieved comparable precision. Maximum accuracy under optimal conditions remained approximately 600 feet, circular error probable at equivalent altitudes. The technological gap that Richter had identified in December 1942 remained throughout the war. The Norden bombsight wasn't just a better bombsight, it was enabling technology for strategic bombing doctrine that won the air war through precision rather than volume. The invisible weapon that destroyed German industrial capacity wasn't the bombs themselves, it was the technology that delivered them with mathematical precision to the exact buildings that mattered most. The technological gap that Richter had identified in December 1942 remained throughout the war. The Norden bombsight wasn't just a better bombsight. It was enabling technology for strategic bombing doctrine that won the air war through precision rather than volume. Richter's post-war debriefing with American intelligence officers lasted 3 weeks. The Americans were fascinated by his December 1942 testing program. They wanted to know exactly what a German bombardier had experienced using the Norden, what aspects had been most difficult to master, what the Luftwaffe had concluded about American bombing capabilities. Richter answered honestly. The device had been intuitive once Fischer understood the basic principles. The difficulty wasn't operating the sight, the difficulty was accepting that such precision was possible. American officers showed Richter classified bombing assessment reports from 1944 and 1945. The data confirmed everything he'd predicted. Mission to Merseburg synthetic oil plants. November 2, 1944. 360. B-17 seconds. Dropped 720 tons of bombs. Circular error probable 83 feet. Production reduced by 92% for 6 months. Mission to Politz Oil Refinery. December 21, 1944. 180 B-17 seconds dropped 360 tons of bombs through solid cloud cover using radar-assisted Norden bombing. Circular error probable 140 feet despite weather. Production eliminated completely for 4 months. The precision had actually improved as the war progressed. Early 1943 missions achieved circular error probable of 200 to 300 feet. By late 1944, experienced bombardiers routinely achieved 100 feet or better. The improvement came from multiple factors. Better bombsight maintenance procedures developed through combat experience, refined bomb ballistics tables that accounted for altitude, temperature, and seasonal variations, advanced bombardier training that emphasized the mathematical principles behind Norden calculations, formation bombing techniques that concentrated multiple aircraft's ordnance on single aim points. Richter learned that American bombardier training had evolved significantly by 1944. Initial 1942 training focused on basic Norden operation. By 1944, training included advanced topics, understanding gyroscopic principles and how aircraft motion affected stabilization, calculating wind drift corrections for varying altitude layers, compensating for temperature effects on bomb ballistics, identifying and hitting specific building features within larger target complexes. The 12-week training program had expanded to 18 weeks for lead bombardiers who would control entire formation bomb releases. The Americans had recognized that Norden precision enabled new tactical approaches. Formation bombing allowed multiple aircraft to release on a single bombardier's signal. The lead bombardier would use his Norden to establish the precise release point, then trigger an electrical signal that released bombs from every aircraft in formation simultaneously. This concentrated dozens of aircraft's ordnance into a single aim point, creating devastating destructive density. German area bombing had never developed equivalent techniques because individual aircraft accuracy was too variable to benefit from coordination. Richter saw reconnaissance photos of specific raids that demonstrated Norden precision at extreme levels. The Dortmund-Ems Canal attack in September 1944 showed what experienced crews could achieve. The canal was 30 meters wide, protected by massive flak concentrations, and required direct hits to breach the walls. American formations made 4 attempts between September and November, dropping progressively fewer bombs as bombardier accuracy improved. The final successful attack in November used only 96 B-17 seconds to breach the canal in 3 locations. Post-strike photos showed bomb craters aligned along the canal walls with spacing measured in feet, not hundreds of feet. The Americans explained their industrial production philosophy. Norden bomb sites weren't just manufactured, they were engineered as precision instruments with rigorous quality control. Every site underwent calibration testing before delivery. Gyroscopes were spun for 72 hours continuous operation to verify bearing stability. Optical elements were tested for alignment accuracy to within 1 arc minute. Mechanical computers were verified by calculating known trajectories and comparing results to ballistic tables. Any site that failed specifications was rebuilt completely rather than adjusted. This quality control meant American bombardiers could trust their equipment absolutely. The site would perform as specified, the calculations would be accurate, the stabilization would maintain alignment. Trust enabled confidence. Confidence enabled the aggressive, high-altitude daylight bombing that German fighters couldn't prevent and German flak couldn't defeat. Richter compared this to German production philosophy. Lotfe 7 sites were built to adequate specifications with acceptance testing that verified basic function. But precision calibration wasn't feasible at production scale. Individual sites varied in accuracy by 10 to 15%. German bombardiers learned to compensate through experience, adjusting for their particular site's characteristics. This worked adequately for area bombing where precision wasn't critical. It was completely inadequate for the precision strikes American doctrine demanded. The industrial philosophy difference extended beyond the bomb site itself. American B-17 seconds and B-24 seconds were built with extensive redundancy, multiple oxygen systems, backup hydraulics, redundant electrical generators. The aircraft could sustain significant battle damage and continue flying. German bombers prioritized performance and payload over redundancy. A single hydraulic failure could make a Ju-88 uncontrollable. The American approach accepted weight penalties for survivability and reliability. The German approach minimized weight to maximize performance and payload. Both philosophies reflected deeper strategic thinking. Germany fought a continental war where bombers could operate from multiple nearby bases. If an aircraft developed problems, it could land at alternate fields relatively easily. America fought an oceanic war where bombers operated hundreds of miles from friendly bases. Redundancy was survival. The Norden embodied American strategic advantages: industrial capacity to produce complex systems at scale, engineering culture that prioritized precision and reliability, willingness to invest development time creating sophisticated solutions rather than adequate solutions, coordination between government and industry that unified specifications and production standards. Germany possessed none of these advantages by 1942. Industrial capacity was fully committed to existing weapon systems. Engineering culture had evolved toward simplified designs that could be produced with limited resources. Government-industry coordination was fragmented across competing agencies and manufacturers. The Norden gap wasn't fixable through German effort. It required advantages Germany didn't possess and couldn't develop under wartime conditions. Richter's final conversation with American interrogators focused on what Germany could have done differently. His answer was sobering: nothing. The Norden represented development begun in the 1930s, refined through years of peacetime industrial investment, and deployed with production capacity built specifically for complex precision systems. Germany in 1942 couldn't replicate 1930s American industrial investment. Even if German engineers had captured a Norden in 1939 and immediately begun development programs, the production infrastructure didn't exist. Building that infrastructure while fighting a multi-front war was impossible. The lesson Richter drew was strategic. Technological advantage in modern warfare came from industrial capacity and long-term investment, not battlefield innovation. Germany had won early victories through tactical innovation and operational excellence, but tactical innovation couldn't overcome industrial capacity gaps of the magnitude the Norden represented. The invisible weapon that destroyed German industrial capacity wasn't the bombs themselves. It was the technology that delivered them with mathematical precision to the exact buildings that mattered most. American strategic bombing didn't win through overwhelming force. It won through overwhelming precision applied to critical vulnerabilities. The Norden bombsight gave American commanders the capability to systematically dismantle German war production by destroying specific factories, specific power plants, specific transportation nodes. German defenses couldn't protect everything simultaneously. American precision meant they didn't need to. Oberst Klaus Richter spent his remaining years analyzing the technological lessons of World War II. He published technical papers on precision bombing, industrial production capacity, and the relationship between engineering, philosophy, and military effectiveness. His central thesis remained consistent. Modern warfare rewards societies that invest in long-term technological development and industrial-scale production of sophisticated systems. Tactical excellence and operational innovation matter, but they cannot overcome fundamental technological gaps of the magnitude the Norden represented. The captured bomb site he'd examined in December 1942 had revealed a truth German leadership never fully accepted. America hadn't just built better weapons. America had built an industrial system capable of producing sophisticated technology at scales Germany couldn't match. That industrial advantage, applied through precision rather than volume, had won the air war before German fighters ever engaged American bombers. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.
May 30th, 1944, 01:44 hours, north of the Admiralty Islands, Western Pacific. Captain Ryanosuke stood in the cramped, conning tower of RO 105, his eyes sweeping the dark horizon through the night periscope. The rubber eyepiece pressed against his face as he rotated the scope through a slow 360-degree arc, searching for any silhouette against the stars. Nothing. The ocean was black and empty in every direction. 12 days earlier, he had departed Saipan as commander of Submarine Division 51, leading 7 boats into position along Scouting Line NA. Their mission was simple on paper: detect any American fleet movement toward the Palau Islands and transmit contact reports to Combined Fleet Headquarters. Admiral Toyoda needed eyes in the water. Ryanosuke and his submarines would provide them. The boat ran on the surface at 12 knots, her twin diesel engines charging the depleted batteries with a steady mechanical rhythm. Below decks, the air was already thick from 18 hours submerged, the carbon dioxide scrubbers saturated, the humidity oppressive. The crew moved through their duties with the careful economy of men conserving strength. Surface time was precious. Every minute topside meant power flowing back into the batteries, fresh air cycling through the compartments, a chance for the boat to recover from the strain of sustained underwater operations. It was also, as Ryanosuke was about to discover, the most dangerous time of all. 6,000 yards to the southeast, the destroyer USS Hazelwood swept her SC-2 radar across the ocean in methodical arcs. The antenna rotated atop the mast, invisible in the darkness, sending out pulses that traveled at the speed of light and returned with information no human eye could provide. At 01:44, the return came back clean and sharp, a contact bearing 270 degrees, range 6,000 yards, surface vessel, small signature consistent with a submarine's conning tower. The radar operator marked the contact on his plotting board and reported to the bridge. Hazelwood's captain ordered increased speed. The destroyer's turbines spooled up, and the ship surged forward through the dark water, closing the range at 25 knots. At 01:53, Row 105's port lookout shouted the alarm, a dark shape against the horizon, moving fast, growing larger. Destroyer Rhinosuka reacted instantly. Dive! Dive! The alarm klaxon shattered the night. Ballast tank vents slammed open. Diesel engines coughed and stopped as the air supply was cut. Electric motors engaged with a whine. The boat's bow angled downward as tons of seawater flooded into the ballast tanks, dragging her beneath the surface. Crash dive procedures for an RO-100 class submarine required 35 seconds from alarm to periscope depth. The boat was 60 meters long, displacing nearly 800 tons submerged. She did not slip beneath the waves like a fish. She forced her way down through sheer mass and flooding, every second of the descent exposed to whatever weapons the enemy might send after her. Hazelwood's sonar operator acquired contact within seconds of RO-105's disappearance from radar. The American destroyer had her. From this moment forward, the hunt would be continuous. What followed would last 30 hours, over 20 separate attacks, and in those 30 hours, Rhinosuka would come to understand what had happened to the 6 submarines from Scouting Line NA that had gone silent since May 19th. He would understand why no distress signals had been transmitted, why no wreckage had been found, why the positions assigned to RO-106, RO-104, RO-116 and RO-108 had simply gone quiet, one after another, in a systematic progression that could not be coincidence. He would understand that the war had changed, and that understanding would come too late to save him. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Scouting Line. NA had been Admiral Somu Toyoda's solution to an impossible intelligence problem. The newly appointed Commander-in-Chief of the Combined Fleet, he had taken the position just 3 weeks earlier, on May 3rd, faced uncertainty that threatened to paralyze his entire strategic position. American forces had advanced across the Marshall Islands in February. They had pushed deep into New Guinea throughout the spring. A massive task force was assembling somewhere in the Central Pacific, its composition and target unknown. Would the Americans strike north toward the Marianas, west toward Palau, south toward the Philippines? Each possibility demanded a different response. Each wrong guess would waste irreplaceable fuel and ammunition while leaving the actual target undefended. Toyoda's mobile fleet was powerful on paper. 6 aircraft carriers, 10 battleships, 40 cruisers, and destroyers. But those ships carried fuel for only one major engagement. The oil situation was critical. Japanese refineries could not keep pace with consumption. If Toyoda sortied his fleet toward Palau and the Americans hit Saipan, he would have wasted his fuel reserve and left the Marianas defenseless. If he held position at Tawi-Tawi and the Americans bypassed him entirely, the fleet would sit idle while the empire collapsed around it. He needed intelligence. He needed advance warning of American movements. He needed eyes in the water that could detect an approaching fleet and report its position, course, and composition before it reached its target. The solution was a submarine picket line. 7 boats of submarine squadron. 7 would take position north of the Admiralty Islands. RO-104, RO-105, RO-106, RO-108, RO-109, RO-112, and RO-116. They would form a barrier across 650 miles of ocean. Each submarine assigned a patrol sector of roughly 90 miles, spaced at those intervals, with overlapping sonar coverage. They would detect any major fleet movement through the area. The boats departed their bases between May 15th and 17th. RO-108, RO-112, and RO-116 sailed from Truk on the 15th. RO-106 and RO-109 followed on the 16th. RO-104 and RO-105 departed Saipan together on the 17th, with Captain Ryanosuke aboard the latter as division commander. They were RO-100 class submarines, medium-sized coastal boats designed for point defense and patrol operations close to Japanese bases, displacing 611 tons surfaced and 795 tons submerged. They were considerably smaller than the large I-class fleet submarines that had attacked Pearl Harbor and hunted American shipping lanes. Each RO-100 measured just under 61 meters in length, with a beam of 6 meters. The crew complement was approximately 55 men, packed into compartments that offered standing room only and bunks shared between watches. The boats were powered by two 500-horsepower diesel engines for surface running and two 380-horsepower electric motors for submerged operations. On the surface, they could make 14 knots and had a range of 3,500 nautical miles at 12 knots. Submerged, they were limited to 8 knots maximum speed and a range of just 60 nautical miles at 3 knots. The slow, battery-conserving crawl that would become so important in the days ahead. Armament consisted of 4 bow torpedo tubes with 8 Type 95 torpedoes, plus 2 25mm anti-aircraft guns. The boats carried no deck gun for surface engagements. They were not designed to fight on the surface. They were designed to hide, to watch, to report. Their maximum diving depth was 75 meters, 246 feet. This was adequate for coastal patrol operations in relatively shallow waters. It would prove catastrophically insufficient against the weapons now being deployed against them. Japanese doctrine considered these boats adequate for the scouting line mission. They did not need to attack the American fleet, only to detect it. They did not need to fight their way out of contact, only to dive and evade long enough to transmit a report. Their role was reconnaissance, not combat. What Admiral Toyoda did not know. What Captain Ryanosuke did not know. What no one in the Japanese command structure knew was that the Americans had read every word of the orders establishing Scouting Line A before the first submarine reached position. On May 18, 1944, Signals Intelligence personnel at Fleet Radio Unit Pacific in Pearl Harbor intercepted and decrypted Japanese naval communications detailing the formation of the picket line. The decrypt included the designation Scouting Line NA, its geographic position between Truk and the Admiralty Islands, the names of all 7 submarines assigned, their departure dates, and their individual patrol sectors. The information reached Admiral William Halsey's 3rd Fleet headquarters within hours. The Americans now knew exactly where the Japanese submarines would be, when they would arrive, and what they were supposed to do. The picket line that was meant to detect American fleet movements had been compromised before it was established. Halsey's staff saw an opportunity. 7 submarines concentrated in known positions, operating under predictable doctrine, could be destroyed systematically before they provided any useful intelligence. The Americans would not avoid the scouting line. They would eliminate it. 3 destroyer escorts received orders at Purvis Bay in the Solomon Islands: USS England, USS George, and USS Raby. These were Buckley-class vessels, 1,400 tons displacement, smaller than fleet destroyers, but purpose-built for anti-submarine warfare. Each ship carried a crew of about 186 men, 3 3-inch guns, various anti-aircraft weapons, and 3 21-inch torpedo tubes. But the weapons that mattered were not the guns or torpedoes. Mounted on the foredeck of each destroyer escort was a Hedgehog anti-submarine mortar, the weapon that would destroy Scouting Line NA. The Hedgehog was a British invention, developed to solve a fundamental problem in depth charge attacks. Conventional depth charges were dropped or thrown from the stern and sides of a ship as it passed over a submarine's estimated position, but sonar could not track a target directly beneath the attacking vessel. There was a blind spot. In the final moments before weapons release, a skilled submarine commander could exploit that blind spot, making a radical course change in the seconds before the depth charges arrived. The Hedgehog eliminated the blind spot by throwing its projectiles ahead of the ship while the submarine was still in sonar contact. The weapon consisted of 24 spigot mortars arranged in rows, each firing a projectile that weighed about 65 pounds with a 24-pound Torpex warhead. When triggered, the mortars fired in rapid sequence, sending all 24 projectiles arcing forward to splash into the water roughly 200 yards ahead of the ship. The projectiles sank at about 23 feet per second, forming an elliptical pattern roughly 43 meters by 37 meters as they descended. Unlike depth charges, which exploded at a preset depth whether they hit anything or not, Hedgehog projectiles carried contact fuses. They exploded only when they struck a solid object, like a submarine's pressure hull. This meant that misses were silent. The projectiles that failed to find the target simply sank to the ocean floor without detonating. There was no curtain of explosions to blind the sonar operators or create confusion about whether hits had been achieved. The attacking ship maintained continuous sonar contact throughout the attack and could assess results immediately. If no explosions were heard, the submarine had evaded. Reload and attack again. If explosions were heard, the submarine had been hit. Assess, damage, and attack again if necessary. The mathematics of this weapon system were devastating. A single Hedgehog salvo put 24 contact fuse projectiles into the water in a pattern calculated to cover the probable location of a maneuvering submarine. Each projectile carried enough explosive to rupture a pressure hull. A submarine at the center of that pattern faced 24 individual chances to die, and because the weapon maintained sonar contact and produced no blinding explosions on a miss, attacks could continue indefinitely at intervals of just a few minutes, the time required to reload the mortar tubes. By 1944, Japanese submarine commanders had learned to evade conventional depth charges. They dove deep below the explosion depths. They maneuvered radically during the attacking ship's blind approach phase. They exploited the confusion of multiple explosions to slip away undetected. Experienced captains could read the patterns of depth charge attacks, predict the timing, and position their boats in the gaps between explosions. Against Hedgehog-equipped destroyer escorts, none of those tactics worked. There was no blind approach phase. The weapon fired while still in sonar contact. There were no explosions to exploit for escape. Misses were silent. There was no preset depth to dive beneath. The projectiles detonated on contact wherever they found the target. The mathematics had changed. The survival calculus had inverted. In the Battle of the Atlantic, where Hedgehogs had first been deployed against German U-boats, the weapon achieved a kill rate of approximately 1 submarine sunk for every 5 attacks. This was roughly 10 times more effective than conventional depth charges, which averaged about 1 kill per 60 attacks. The numbers told the story. Hedgehog-equipped ships could destroy submarines with systematic efficiency that traditional anti-submarine weapons could not match. Now those weapons were coming to the Pacific. The 3 destroyer escorts departing Purvis Bay on May 18th all carried Hedgehog mortars. Their crews had trained extensively in anti-submarine warfare procedures. Their sonar operators were experienced. Their commanders understood the tactical doctrine of hunter-killer operations, and they knew exactly where their targets would be. The hunter-killer group's first objective was not part of Scouting Line NA. On May 13th, Fleet Radio Unit Pacific had intercepted a transmission from I-16, a large Type C fleet submarine, reporting her estimated arrival time at Bougainville, where she was scheduled to deliver supplies to Japanese troops. The decrypt gave position, course, and timing. The 3 destroyer escorts would intercept I-16 first, then turn their attention to Scouting Line NA. On the afternoon of May 19th, USS England's sonar detected I-16 north of Bougainville. The submarine maneuvered skillfully, using a tactic that had worked against depth charge attacks. She followed in England's wake, staying directly astern where the ship's own propeller noise masked the submarine's sound signature and made sonar tracking difficult. England's first Hedgehog attack missed. The submarine had not been where the sonar operator predicted. Second attack missed. Third attack missed. Fourth attack missed. I-16's commander was experienced and aggressive, exploiting every advantage his boat possessed. On the fifth attack run, England's Hedgehog salvo found the target. The crew heard 4 to 6 detonations from below, the unmistakable sound of contact-fused projectiles striking a pressure hull. 3 minutes later, a massive underwater explosion lifted England's fantail out of the water and shook the entire ship. The submarine's hull had imploded under depth pressure, or her torpedo warheads had detonated. Debris rose to the surface 20 minutes later. I-16 was gone with her entire crew of approximately 100 men. The first kill had taken 5 attacks. It had cost no American casualties, no expenditure of torpedoes, no air support. The destroyer escort had simply detected the target, tracked it through evasions, and fired until the mathematics produced a hit. Now, the 3 ships turned north toward Scouting Line NA. The submarines of the picket line were arranged along their assigned barrier at intervals of roughly 90 miles. The Americans planned to find the easternmost boat and work their way west along the line, destroying each submarine before it could warn the others or report the attack to combined fleet headquarters. The key was speed and systematic execution. Find the target, attack until destroyed, move to the next position, repeat. At 0351 on May 22nd, USS George detected RO-106 on radar at a range of 14,000 yards. The submarine was on the surface, charging batteries, her crew unaware that their radar detector had failed to pick up the American emissions. George's radar operator tracked the contact as the range closed. At 5,000 yards, the destroyer escort illuminated RO-106 with a searchlight. The submarine crash-dived immediately, but the American ships already had the position. George's sonar operator acquired contact within seconds, and the destroyer escort began her attack run. The first Hedgehog salvo missed. RO-106's commander had maneuvered hard as he dove, throwing off the sonar prediction. England moved in to assist. Her first salvo missed. Her second salvo at 0501 scored at least 3 detonations. The crew heard the hits, then the secondary sounds of a submarine breaking up, the groaning of metal, the collapse of compartments, the rush of water into spaces that had held air. A large underwater explosion followed as RO-106's remaining airspaces collapsed or her ordnance detonated. RO-106 sank, with all 49 members of her crew. Time from first radar contact to confirmed kill, approximately 70 minutes. The first boat of Scouting Line NA was gone. The 3 destroyer escorts formed a search line and swept northwest toward the next position. On May 23rd, the Americans found RO-104. The submarine had been on station since the 17th, faithfully executing her patrol duties, watching for the American fleet that was supposed to pass through her sector. She never saw her killers coming. George and Roby made the first attacks. Between 0617 and 0810, they fired 8 Hedgehog salvos at the maneuvering submarine. All missed. RO-104's commander was skilled, using radical depth and course changes to throw off the sonar predictions, keeping his boat alive through the barrage. At 0819, England took over. Her first attack missed. Her second salvo scored 10 to 12 detonations at a depth of 300 feet, well beyond RO-104's rated maximum depth of 246 feet. The submarine had gone deep in her evasion attempts, diving past her tested limits, and the Hedgehog projectiles had followed her down. England then dropped a pattern of 13 depth charges set to explode between 350 and 450 feet, ensuring the destruction of any compartments that might have survived the initial hits. Debris and oil reached the surface At 10:45, RO-104 was confirmed destroyed with all 58 hands. 2 submarines sunk in 36 hours. The Americans were working through Scouting Line NA with methodical efficiency. On May 24th, George detected RO-116 on radar at 0120, another submarine on the surface, charging batteries under cover of darkness, trusting that night would provide concealment. The Americans did not need light. Their radar saw clearly in any conditions. England gained sonar contact at 0150 and attacked at 0214. 3 to 5 detonations. The crew heard breaking up noises, but no major explosion. The submarine had been crushed rather than blown apart, her pressure hull failing under the combined stress of hedgehog damage and depth. Oil and debris appeared at sunrise. All 56 members of RO-116's crew were lost. 3 submarines destroyed in 72 hours. The mathematical progression was relentless. The Americans had suffered no casualties, expended no irreplaceable munitions, lost no time to repairs or resupply. They had simply appeared, detected, and killed with systematic precision, and they were not finished. On May 26th, the destroyer escorts put into Seidler Harbor at Manus Island in the Admiralties to replenish their Hedgehog ammunition. The weapons had performed exactly as designed, but the rapid succession of attacks had depleted the ship's magazines. While in harbor, a hunter-killer group arrived. The escort carrier, USS Hoggett Bay, with destroyers Hazelwood, Heermann, Hole, and McCord, plus the destroyer escort Spangler. The combined force got underway almost immediately. There were more submarines to find. On the evening of May 26th, during the transit back to the patrol area, England's sonar operator detected another contact, RO-108, the 4th submarine of Scouting Line NA. At 23:04, England fired her first Hedgehog salvo, direct hits on the first attack. The crew heard 6 to 10 detonations, followed by the sound of a hull collapsing under pressure. A massive underwater explosion confirmed the kill. RO-108 was destroyed with all crew members, the same boat that had torpedoed the American destroyer USS Henley the previous October, one of the few successful attacks by a Scouting Line NA submarine against American warships. 4 submarines sunk by a single ship in 8 days. USS England had now destroyed I-16, RO-106, RO-104, RO-116, and RO-108. The mathematics were catastrophic for the Japanese picket line. Of the original 7 boats assigned to Scouting Line NA, only 3 remained. 2 of those, RO-109 and RO-112, had already withdrawn. On May 27th, Japanese 6th Fleet intelligence had intercepted and partially decoded American naval communications. The messages were described as increasingly jubilant, containing references to multiple submarine kills in the area north of the Admiralties. 6th Fleet transmitted a warning to all boats on the scouting line. American anti-submarine forces active in your sector. Multiple boats unresponsive. Exercise extreme caution. RO-109 and RO-112 received the warning and cleared the area immediately. They would survive. RO-109 until September 1944, RO-112 until February 1945, when she was sunk by USS Batfish off Luzon. That left only 1 submarine still on station. RO-105, Captain Ryanosuke, commander of Submarine Division 51, the most experienced officer remaining from the entire scouting line. The communications from 6th Fleet headquarters on May 27th had been ominous, but not decisive. Multiple boats, unresponsive. American signals increasingly jubilant. Exercise extreme caution. Maintain mission, unless otherwise directed. Ryanosuke had not received orders to withdraw. He was the division commander. If anyone should hold position, it was him. Scouting Line NA still existed in theory, even if only 1 submarine remained to maintain it. For 3 days after RO-108 went silent, he held his position. He did not transmit. He understood now that radio emissions were death sentences. He charged batteries only at night, limiting surface time to 3 hours maximum. He listened through his hydrophones for the high-frequency whine of American sonar, the rhythmic beating of destroyer propellers. He heard nothing. By May 30th, RO-105's batteries were dangerously depleted, down to 40% capacity, enough for perhaps 6 hours of submerged operations at slow speed. The air was foul, the carbon dioxide levels climbing toward dangerous thresholds. Rhinosuke had no choice. At 0100 hours, he brought RO-105 to the surface and began charging. At 0144, Hazelwood's radar found them. The crash dive was executed perfectly, 35 seconds from alarm to periscope depth, but by the time RO-105 passed 50 meters, Hazelwood had sonar contact. Rhinosuke ordered radical evasive maneuvers, hard right rudder, increased speed to 6 knots, dive to 70 meters, near the boat's maximum rated depth. Hazelwood's first depth charges exploded above and behind them, shaking the hull violently but causing no serious damage. The charges were set too shallow. The submarine was below the blast radius. At 0435, George and Raby arrived. The hunt escalated. Rhinosuke heard the new propeller signatures through his hydrophones. 2 more ships moving into position around his submarine. The first Hedgehog salvo splashed into the water at 0452, 24 distinct splashes in rapid sequence. Then silence as the projectiles sank toward RO-105's depth. He ordered hard right rudder. The submarine began to turn. Silence. No explosions. The salvo had missed. The mathematics of survival were brutal. Each attack put 24 contact-fused projectiles into the water in a pattern designed to cover a submarine's probable position. If RO-105 was inside that pattern, she would be hit. If her maneuvers carried her beyond the predicted position, the projectiles would sink past harmlessly. Second salvo at 0508. Rhinosuke jinked left. Silence. Miss. Third salvo. Fourth. Fifth. The attacks continued through the pre-dawn darkness, salvo after salvo, splashing down, sinking through the black water, missing by meters as Rhinosuke maneuvered desperately. Some salvos came close enough that he could hear the projectiles rushing past the hull. Others fell farther away. At 0615, George appeared to score hits, 3 explosions in close sequence. Rhinosuke felt the shocks through the hull, but RO-105 did not die. The boat was wounded, cracks in the forward ballast tanks, seepage in several compartments, compromised trim, but still functional. Still alive. He kept fighting. The hours passed. The attacks continued. Inside RO-105, the air grew thick and poisonous. Carbon dioxide levels climbed past 4%. The batteries drained with every maneuver. The crew worked in near silence, movements sluggish, thoughts clouded. They knew the mathematics were against them. They kept working anyway. At 0500, on May 31st, more than 27 hours after the hunt began, 2 more ships arrived, Spangler and England. Commander Hamilton Haines had ordered England to hold back during the initial attacks. The ship had already sunk 5 submarines. There was sentiment that other vessels should have their chance. But RO-105 had survived over 20 attacks across 27 hours. This was not a boat that would be destroyed easily. Spangler attacked first. Her Hedgehog salvo missed. Haines radioed, "Oh, hell! Go ahead, England." Lieutenant Commander Walton Pendleton positioned his ship for attack. At 0729, England gained solid sonar contact. At 0736, England fired. 24 Hedgehog projectiles arced from the foredeck mortars, splashing down 200 yards ahead. They sank toward RO-105's depth. Rhinosuke heard the splashes and ordered another turn, hard right rudder. The maneuver that had saved them so many times. But the mathematics had finally caught up. The pattern was positioned differently. The timing was better. Or the accumulated damage had slowed the boat's response, left her inside the kill zone by meters that mattered. 6 to 10 detonations. The explosions tore through RO-105's pressure hull in multiple locations. Seawater blasted into the boat. Electrical systems failed. Bulkheads collapsed. At 0741, a massive secondary explosion marked the end. RO-105 broke apart in the darkness. Captain Ryan Osuka and all 55 members of his crew died instantly. They had fought for 30 hours. They had evaded over 20 Hedgehog attacks. They had prolonged their survival far beyond what probability suggested was possible. It was not enough. In 13 days, USS England had sunk 6 Japanese submarines, I-16, RO-106, RO-104, RO-I-116, RO-108, and RO-105. 328 Japanese submariners had died. No American had been killed. Admiral Ernest King responded, "There will always be an England in the United States Navy." If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The tactical implications were severe. Admiral Toyoda had lost his early warning system. When American forces invaded Saipan on June 15th, just 16 days later, the combined fleet had no submarine screen to detect the approach. The Battle of the Philippine Sea followed, becoming known as the Great Marianas Turkey Shoot. 4 Japanese carriers were sunk. The destruction of the scouting line had blinded the fleet at the moment it needed to see most clearly. But the strategic implications went deeper. The systematic destruction of Submarine Squadron 7 demonstrated that the Japanese submarine force was no longer capable of operating effectively against American anti-submarine forces. The technology gap had become insurmountable. By the end of 1944, Hedgehog mortars would be standard equipment throughout the Pacific Fleet. The mathematics of anti-submarine warfare had shifted permanently. In the Battle of the Atlantic, Hedgehogs achieved approximately 1 kill per 5 attacks, 10 times more effective than conventional depth charges. Now, that effectiveness was being applied to Japanese submarines with devastating results. The Japanese submarine force entered the war with 125 boats. By war's end, 130 would be lost. More than 80% of Japanese submarines commissioned during the war never returned from patrol. The RO-100 class boats that made up Scouting Line Ne exemplified the problem. Their maximum diving depth of 75 meters was hopelessly insufficient against weapons that could reach targets at 90 meters and beyond. The human cost was staggering. Of approximately 25 Japanese submarines deployed during May and June 1944, about 17 were sunk, a casualty rate exceeding 60% in 2 months. Experienced commanders who had survived since Pearl Harbor died alongside green crews on their first patrols. The loss of institutional knowledge was catastrophic. Captain Ryan Osuka had done everything correctly, according to Japanese doctrine. He had maintained his position. He had preserved radio silence. He had limited surface time. He had maneuvered with extraordinary skill. None of it mattered. The doctrine was no longer survivable. The American advantages were comprehensive and mutually reinforcing. Signals intelligence compromised Japanese communications before operations could be executed. Radar detected surfaced submarines regardless of darkness. Sonar tracked submerged contacts with improving precision. And forward-throwing weapons delivered contact-fused explosives with accuracy that conventional depth charges could not approach. Against this integrated network, Japanese submarines had no effective counter. They required radio communication, but transmissions revealed positions. They required surface time, but surfacing exposed them to radar. They required air, but extended submergence meant poisoning. The fundamental physics of submarine operations had become fatal vulnerabilities. The statistics tell the complete story. By the end of the war, Japanese submarine losses would total over 10,000 men killed in action. Only the kamikaze pilots suffered a higher casualty rate among Japanese military services. The submarines of Scouting Line NA rest in the darkness north of the Admiralty Islands, their hulls scattered across the ocean floor. RO-106 with 49 dead, RO-104 with 58, RO-116 with 56, RO-108 and RO-105, the submarine that held out longest, fought hardest and died last. Captain Ryan Asuka receives no memorial outside naval records. His name appears in documents associated with Submarine Division 51, listed among officers lost with their commands. But his story illustrates a truth that transcends any single engagement. Wars are not won by courage alone. They are won by the integration of technology, intelligence, industry, and doctrine into systems that overwhelm individual skill. Ryan Asuka was skilled and determined. He evaded over 20 attacks through superior seamanship. He demonstrated every quality that Japanese military culture valued. And he died anyway, because the system arrayed against him could not be defeated by individual excellence. The Americans had broken his codes. They had detected his boat with radar he could not see. They had tracked him with sonar he could not confuse. They had attacked him with weapons he could not evade. 24 projectiles per salvo, continuous attacks for 30 hours. One submarine remaining when the hunt began. 0 surviving when it ended. The mathematics were absolute. USS England did not survive the war unscathed. On May 9th, 1945, she was hit by a kamikaze off Okinawa, killing 37 sailors. She was never fully repaired and was decommissioned after the war. But her record stands. 6 submarines destroyed in 13 days, an unbroken achievement in anti-submarine warfare history. The ship that proved what integrated hunter-killer operations could accomplish against an enemy submarine force. Captain Ryan Asuka's RO-105 still rests on the ocean floor, her pressure hull shattered, her crew entombed in their final patrol. They were sent to watch for an American fleet. They found hunter-killer groups instead. They fought for 30 hours against weapons that gave them no chance. The weapon that killed them was simple, accurate, and relentless. It did not require exceptional skill to operate. It required only mathematics and the willingness to fire again and again and again until the target stopped moving. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.